Well, hello friends. Today we are going to work on visualizing memory usage a little bit. And specifically I want to show within regions of memory which parts of them are being used, because that's something I've always been kind of curious about, and I feel like no tools I ever used let me see that. So now that we make the tools, we can visualize whatever we want. So basically, for example, here we have the stack, right? And it's 4 megabytes in size, but there's only 12 kilobytes of it that are actually resident. And I would like to see which 12 kilobytes they are. So what I'm thinking is we'll put like a new column here, and it will be a graphical view, and it will just be sort of a bar, and each column will represent a percentage of the region, and then we'll just fill in the parts that are resident and leave white the parts that are non-resident. And that should give us the ability to sort of see which piece of a region is actually resident in physical memory. And then we could maybe write some test program that allocates a large piece of virtual memory and then fills it up slowly, and we could see how it actually looks in physical memory. And it's just something that I have a feeling will be interesting, because I always think that visualizing things can allow you to gain insights that you wouldn't otherwise get just by hooking into your brain's pattern matching abilities. And this is all just a theory, but we're just going to try it out. So, and then just see if it tells us anything interesting, or even if it just looks neat. Then maybe that would be a reason enough. So the first thing we'll need to publish this information so that we can pick it up. So currently what we do have is we have some stuff in /proc. So if we go and look at this terminal, for example, PID12, we have, so everything that we saw there in the system monitor, it comes from the proc PID VM. So if we JP this guy, we can see that it's all JSON, and it's just for each memory region we have this metadata about each one, right? But we don't actually see here which parts of this region are used or are resident and which ones are not. We just see that like there's a certain amount resident and a certain amount dirty, and then there's the size of it. So what do we do? One thing that we could do is we could just add an array to this metadata that would just contain like true or false for each page. So, but let me just show you, we do have also, oh right, I have to be root to look at this because it, wait, what the heck did I just do? I wanted to show VM objects. Oh, this doesn't look quite right at the bottom here. That was weird. Terminal issue. Anyway, so this file is called VM objects, and it's not updated for JSON, but we can see here, so this is an individual region, and it's actually, I mean, this is a VM object specifically, and it's a shared buffer, so maybe it's easier to look at this guy here. So this is a 64 kilobyte malloc block with 128 byte chunks, and these are all of the physical pages inside of this malloc block. So these are the physical addresses of each page, and then the 1 is the reference count. So we can see that this one has a physical address for each of its page slots. Whereas if we, let's see if we can find something else in here that's not completely filled. Yes, this guy right here. I think this is a stack. Yeah, it's a stack. So we got our 4 megabyte stack, and we can see that This exclamation point, I think means that it's copy on write, if I recall correctly. That was forever ago that I implemented this file. But anyway, we can see that we have the same physical address recurring many, many times, and that's the zero page, the shared zero page. So that's the page that we default to when something has never been used. So we just have a globally shared zero page that I actually implemented that a couple of videos ago. It's just to optimize the case where if you read from that memory, you'll just get zeros and we don't have to deal with a page fault. It's only when you write to it that we actually do something in the kernel. But anyway, what I wanted to show here is just that we have this data, right? So we just want to surface it, but this is not super friendly. So it would be better if we could integrate it into this here. And an array might be a pretty straightforward way to do it, but it would also be very heavy, I feel like, because say that you have like a 4 megabyte thing, right? So that's 4 megabytes, and then how many pages are that? It's 1024 pages, right? So there would be an array of 1024 bools in JSON. So you can see how this would quickly become obnoxious if you start to scale up. If you go to a, I don't know, 128, and you get this many bools in an array. So one option would be to do a string that's just like a long string that's like, I don't know, 0 or 1, and it would be 1 character per page, for example. Maybe that's actually the easiest. Maybe we should do that. As I was thinking, we could also do like, you could put out 32-bit values, and they would have 32 bits representing 32 pages in each one, and da 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 da. But I think the string would be the most straightforward, so let's do that. So we'll have to go in procfs, because this is where we generate that file, and it will be in pid VM. This is the function that generates proc_pid_vm, and it's using a JSON array serializer. So we will just let's see, how do we do this? We want to build a new string here, so string builder. Or does this thing allow us to append? We can append directly to him as well, although that's a bit sketch. So let's use the string builder for now. So we'll call this guy the page map builder. And maybe a page map. Is this really even a page map page array? But we're not making an array. We'll call it the page map. I'll live with it. Okay, and then we want to iterate over all of the pages in this region. So page index is region dot first page index, and as long as the page index is less than a region page count page index. Oh wait, hold on. What am I doing? First page index plus page index. Okay, that's a little bit obnoxious to loop like that, but I think it's maybe okay. Because then, like, wait, why does this look so goofy? Oh, I have too many of those. Another option for looping would be to do something like this, right? You would do 0, and you would loop until the page count, and you would just increment I like that. And then you would say auto page index is region first page index plus I. Okay, well, I immediately like that better, so there we go. And then page map builder, append, and now we just need to look at the page slot for each page of the region. So physical page slot is region VM object physical pages page index. So page index here actually is the index into the VM object. So if you saw my video I did a while back on the architecture of the virtual memory in Serenity, then you're familiar with this, or if you work on it, then you're also familiar with it, but maybe I still have the slides that I made here somewhere. God, I forgot how these were like. Okay, so yeah, so a region is one of these guys, right? And it represents a chunk of the virtual address space in a process. As we can see here, each process has multiple regions, and every region points to a VM object. And then there are various kinds of VM objects. They can be file-backed or anonymous, just RAM-backed, basically. And then each region points into a specific slice of a VM object. So sometimes they represent an entire VM object, but sometimes they only represent a part of the VM object. And the first page index of a region is the index of the physical page. So in this case, this region here, his first page index is 1, because this is physical page 0, this is physical page 1, and this region starts at 1, so that's his first page index, whereas this guy right here would start at 3, right? Because that's his first physical page in the VM object. Anyway, and then, yeah, of course, I was going to say the VM object is who actually contains the physical pages. So now that we want to visualize what this region looks like, we have to go and look at the physical page slots in the VM object. So that's what we're doing now. And it was nice to have a visual aid on hand, actually. Maybe I should make more of those. So physical page slot is wait. If physical page slot, so this is just a ref putter. So if it's null, then we will dump out an n, say. There's no page there whatsoever. And else if physical page slot is the shared 0 page, then we can say that we have a 0 page there that you could read from if you want. Else, then we just have a regular physical page. We'll call that P. So 3 possibilities. Either there's no page whatsoever. So this is the state that we'll be in for an inode-backed VM object, because we don't actually load anything into those until you access them. And then once you access them, we get a page fault, and then we read from the disk. And then we populate the VM object with whatever was in that file on disk, right? So, and then, yeah, like I mentioned, the shared 0 page is special. Okay, so then once we've built up this string, then all we need to do is add it to the region object. So we'll call it page map to string, and maybe that's everything that we need to do, actually. Let's find out. So our terminal is pid12 again. And now we have a page map. So we can see this guy is all physical pages. This guy is a bit more interesting. So he has 3 physical pages followed by a 0 page, and then another physical, and then a 0 page. So definitely an more interesting pattern. These are all single pages. Oh wait, this is obnoxious. Like, I have shift page up and page down to scroll, but when I press shift, it acts like I'm typing and it scrolls to the bottom. I don't want that. On this one is an inode. We can see because he has null pages, so the first time that you actually try to read this memory, the kernel will have to load it from disk. So pretty cool. And here's the stack. We have one physical page at the bottom of the stack, followed by all these shared 0 pages, and then 2 physical pages at the top of the stack. So this guy at the bottom of the stack here, this actually is a little quirk about Serenity. We when we launch a new process, then we store all the arguments here at the bottom of the stack, and it's really just like that because I was a bit lazy when implementing it, and doing it that way was a bit more straightforward than computing all of the space requirements and then putting everything at the top of the stack. But that's something that we could and probably should fix, because it's really weird that you have this region with some stuff at the bottom and some stuff at the top, because then you could imagine that you use more and more stack, and then eventually you would have enough stuff on your stack that you reach here, and then suddenly you start overflowing your arguments to main. You know, that could have some interesting side effects. So even the potential vulnerability there, I should probably fix that. Anyway, but I want to visualize it a bit better than that. So let's do something in the system monitor so we can see this stuff now. System monitor, main. So actually, let me show you. We already have one thing that's sort of in this vein. If we go on the File Systems tab, we can see that these here, they have custom rendering, although they're not displaying. They're supposed to be showing a progress bar indicating how much of the disk is used, but it's not working right. What the heck is up with that? File system, no, what's that thing called? Disk system monitor. Let's find out. Devices. Oh shit, I don't remember what this thing is called. Maybe it's just in the main file. GB. Okay, human readable size. It's in the File Systems tab. Okay. So just to remember how this stuff works. Right, so we have this thing called a cell painting delegate, and that we install on this table view here. So table view has a feature where you can install a delegate object that for a specific column, and then when painting itself, once we get to the specific column here, because it's installed on column number 3, so 0, 1, 2, 3, then painting will actually call this delegate and ask it to do the painting on its behalf. And then the progress bar painting delegate is supposed to know how to paint a progress bar, but something here is not working right. We can see that it's calling paint progress bar and passing in the text, and we do see the text in the middle, so it seems like maybe the percentage is just broken. And we get the percentage by asking the model for custom role data. So, and who is the jerk that's messing that up? What is our model? It's a JSON array model. Oh, how does this work again? Then we have the custom thingy. Okay. So this guy here, this is JSON array model is this very very Serenity idiomatic thing where you can define a data model that is fueled by the contents of a JSON file, and then you're able to put that JSON array model along with the description of the fields that you want to extract, and you can just install that into a table view. So that's what we're doing here. We are just serving up data from I think procdf, right? Yeah, so this is this JSON file sort of filtered through a JSON array model to produce this table. But why do we not compute the percentage correctly, I wonder? It's the total block count. What is the total block count for these guys? So if we're looking at slash, for example, total block count is this. And the free block count is that. Free block count, free block count. I don't know why that would not work. Okay, well, I think maybe I'll just ignore this right now because I want to make a new painting delegate for the memory stuff. So let's get into that instead. So this would be in the process memory map widget, which is also using a JSON array model. So we'll say here m table view set cell painting delegate for column number I guess, oh, we should make a new column for this. We can put him, I don't know, maybe, should we rearrange this a little bit? We can put the cow pages at the end after name, and then we can put the beautiful imagery at here, like right before name. So that would be 0, 1, 2, 3, 4, 5, 6. So cell painting delegate for column 6 is going to be a page map painting delegate. Okay, and actually let me go and steal that delegate that we had. Because even if it's not painting right, we can at least borrow the code here. So page map painting delegate. And I think we'll need libgfx palette. Okay. And we'll also need painter. So there we go. So how are we going to draw this guy? I guess we the page map. How do we extract the page map? Well, we'll just get out the custom data, and in our case, this will be a string page map. And here, instead of this, we can just do like painter draw text in the rect, and then we'll just draw the page map text for now, just to start with. And we'll see what we can come up with here. Data is string as string. I don't know what that is. I don't want none of that. Okay. So system monitor, sync and run. And oh, we didn't need the palette actually. And oh, I'm not setting anything up here correctly either. So this will be the field page map. We'll call it page map like that. And text alignment does not really matter. but then we'll start to do some callbacks. So what are these callbacks? I have to look them up. So the first callback is for the display role, and then there's the sort role, and then finally the custom role. So in our case, we don't care about the display or sort roles. So for those, we can just return a gvariant, I think is the thing that we're supposed to return. Oh no, it's not called gvariant anymore. It's GUI variant. Okay, and there we go. And then this will be our, oops. I think this will be our custom thingy. So we're gonna get called here with a JSON object, and then we have to get the page map out. Wait, how does this work again? I have to look at this guy. Right, we don't specify page map like this, but instead we just get the JSON object, and then we have to know how to fetch out the stuff that we want. So get page map to string. Okay. Do we have an option as string or? We can do this one as well. As string or null string. And then page map. This will be our custom data. Okay. All right. So we got this really awful looking thing here, but we are definitely painting using a custom painting delegate, and you can see that we are just drawing this stuff. So our code is being called, and now we just gotta visualize it a bit better. So, I feel like I've done this many times before, but I always forget how to do it, so bear with me. I guess we want to take a float and what is this thing that we do? We have to go pixel by pixel, right? So for int x is a rect, or we can go like this. X. No, let's go like this. X, let's go like this. Width plus I. And we're going to draw one column at a time, and then the x value here is a rect x plus I, and now we have to look at we have to scale this. So float scale is, or the scale factor or whatever, I don't know, we'll just call it scale factor, is the width that we have and divided by the amount of data that we have, right? So that's the a rect width divided by page map length. Okay. And then char C is page map at float x times scale factor wait, no, it's I times scale factor. So like that, and not printf. Then we'll do painter draw a line from x and the, oh wait, hold on, I shouldn't use a rect, I should use rect, because rect is the one that we've massaged here to shrink it a bit. So we should use rect width and rect y, and then the second point will be x and rect bottom. So we can actually say rect top here. And then we just need to provide a color. So maybe we can do it this way. Switch C case. Oh no, let's do it this way. If C is N, color is going to be cyan. As if C is 0, then we can make it a pleasant blue. And for the physical page, let's do black. Maybe null should be white, actually, because that means that there's nothing there. And maybe this guy should be cyan. So null, no page at all, typically inode, fact mapping hasn't been paged in, no back paged hasn't been paged in, yeah. 0, shared globally, shared 0, page, typically untouched anonymous page. Physical, a resident page. Okay, so this one we'll just say else assert not reached. All right. I feel like I'm messing something up. Yes, I did. The string, we're indexing into the string wrong. Did I do this upside down? Did I do it upside down? What is the scale factor? The width divided by the page map length. See, I'm indexing into the page map, so it's really the page map length that needs to be divided by something, right? Zoom. Oh, and then we're still doing the text. Stop doing the text. And try again. All right, so show me the system monitor. All right. So, I guess you need a ton of pixels if you want to see the tiny amount of stack space that's used at the end there. So these guys are all full. Oh, these guys look kind of interesting. So the black is memory that's backed by physical pages, and the cyan is the memory that is the shared 0 page. So it's not touched. So it's not actually costing us any physical memory. And here we have a file back mapping where we've mapped the font, but we haven't actually used the whole thing because I guess the file is, how big are these files? Res fonts. Oh man, I have so many fonts here. Which one was this? It's Chilla Bold. Alright, so Chilla Bold. It's right, it's 10,319 bytes. So it makes sense that since we operate on a page size in some page size increments here, we're forced to allocate 12 kilobytes of memory, but we only use the first 10 or so. So we end up with the last one is never used, I guess because we never actually read from the tail end of this guy. Probably because we never used the glyphs at the highest part of the glyph space. Because if you look at these fonts here, then these are all laid out in memory. Like this is like early on in the file, and then we progress through the file, and then these are at the end of the file. And because we're not using these goofy symbols, then we're not actually paging that in. Where did you go? So that's kind of curious. Anyway, and then we have here, oh, this one looks really neat. This is the executable that we're running. So system monitor executable, you can see here that since we demand loaded, we've only actually loaded from this part that we need to execute. So I'm guessing that maybe this stuff is like code that we didn't run yet in this program. And this stuff here might be symbol tables or something like that. So in fact, maybe we can get it to load symbol tables. Or I would assume that it has already, since we're producing the backtraces. Yeah, I'm not sure. I'm not sure what that stuff is at the end of the file. Maybe we can find out here. What's at the end of system monitor? System monitor. I guess we can read L -L. It's not terribly fascinating. So these are the sections, and then offset into the file. At the very end, we have the section header string table, and the string table is gigantic. So I don't know what else would be at the end of this file, actually. Let's hex dump it, see what's in there. Well, it's this, whatever this is. Seems like we're not interested in that. And also, when we symbolicate, we have a huge symbol table, right? And when we're symbolicating for the stack traces, then we're only fetching the symbols that we actually need. So just because we are generating the stacks doesn't mean that we are loading the whole symbol table. So anyways, pretty cool. I wonder if we can, if we load another one, then we'll be using the same underlying VM object, and then we could sort of do this to get it to cover more parts. Could you see that some parts became curious? I wish I could make the whole thing come back, but I guess I can't. Anyway, interesting. So I like it. And maybe we can look at some other programs. But what else can we do? It would be cool if we could, let's make a test program to exercise this little thing. So we'll call it userland grow. I don't know what I'm going to call it, so I'm going to call it Easter, because Easter is coming sooner or later. So this will be the name of our program for some reason. Easter. This is pretty cool, by the way. I'm really liking the way this is turning out. And then we'll just make a mapping. So P is and we will map 1 megabyte. Oh, wait, what comes first? Prot read, prot write, map anonymous, map private. Okay, and then we will do something like this, where we just I is less than 1 megabyte, and I plus equals 4096, which is the page size. And then here we will do something like pi is x. So this will touch the page and force the kernel to allocate a physical page for that page slot. And then we can do a little usleep here. So sleep like sleep like a quarter second or a fifth of a second. That will give us some time to look at this, because we'll have we'll have 256 opportunities to see this. I think that'll be interesting. So we'll bring this guy up, and we'll start the Easter program, and then we can see here, this is the mapping, and you can actually see it filling up. It's pretty cool. And if we make it a bit bigger, so this, you can see here live the kernel allocating physical pages because the program is touching that memory. So this shared 0 page is not good enough, since now we're writing something other than the 0. It's pretty neat. I don't know about these colors though. Their colors are a little bit weird. I feel like maybe we should do a very faint color for this one. So we can do a fainter bluish color. What's a good one? We'll go from RGB, and we'll say CoFF. CoFF. Wait, that didn't change at all, because I didn't recompile the thing I wanted to. Come on, Easter program. Ploof. Okay, so now we got this faint and dainty bluish color representing the shared 0 page, because it's really basically very similar to the null page. It's just a little bit different color so that we know that it's a different thing. This is so neat. I wonder if we can see something interesting happen with some other program. Let's get the browser up and going. Look at him. See if we can see something fun here. Oh, what happened? Stay on target, please. And of course, we can't see all the processes. We can only see the ones that we own, but it's still interesting. Oops. So, what can we learn here? Can we open something else up? Wait, what the heck just happened? The browser died? Okay, I guess we had to crash. Never mind, we have to get back to the new browser. Alright, now we are on the web. And can we see something fun? Let's open that big page. Did that just crash the machine? Dang it. Wait, let me out of there. What happened? Unhandled vector 15. Liav, what is this? Well, it seems like we have some bug here. In the new interrupt sharing code, probably. But I want to get back to that page. Oh, wait. Actually happens again. What is that? Happens every time? Okay, well that's not good. Definitely have to fix that. But that's not what we're here to fix today. So let me just try something. I don't have to try more things. I know that this is good now. I like it. I don't know. Just whenever I get these interesting visual toys, I just tend to get a little carried away. So I think we'll move the cow back over there. It was a bit weird to put it to the right of the name, so let's change that. Wonder what that interrupt sharing problem is. I'm sure that the app can figure it out pretty quickly. He's the one who's been working on it lately, improving our support for more interrupt controllers so that we can expand to more hardware. So what's fun to look at? CPU graph, this guy up here. It's interesting that we have kind of weird space utilization in the malloc blocks. We end up with a bunch of slack for some reason. I mean, probably this is because this size class, we never allocated enough to fill this block, so it has like, it only has the free list taking up the space. Anyways, I have to stop saying anyways. Here we can see the audio menu applet has barely loaded himself. Like the executable is not super loaded. Wait, why can't I drag these? Wait, I'm supposed to be able to resize the columns. Oh, dude, there's a bug here. If we scroll down, then you can't resize the columns. Well, that's not right. Oh, I feel like I caused that. I definitely did. Dang it. Okay, let's commit what we have. So add file system procfs expose the underlying physical page map of each region in proc VM. You can now see the state of each physical page slot, each underlying physical page slot in a VM region. Okay, and then we will commit this guy right here. So system monitor, visual add page map visualization for VM regions. This patch adds a new column to the process memory regions view in system monitor. It's a scaled view of the page, underlying page map of the region that tells you which chunks of the region are which chunks are resident, non-resident, 0. Which are resident, which are what? Resident, null, 0. Okay. And that goofy issue where you scroll down and it doesn't let you do this anymore. I feel like I broke this just the other day. Table view. This is in the abstract table view, I think. Mouse down event, mouse move probably. We'll start in mouse move. So let's see. Mouse move. Column resize scrollable rect. So the problem is that event handling in the table view has to take the scroll offset of the table view into account, because you can scroll the table view both horizontally and vertically. So when we're handling mouse events, because we need to know where you're clicking exactly, then we have this thing called the adjusted event position. And the adjusted event position is just where you click and then offset by the scroll delta for the horizontal and vertical scroll bar. But when it comes to figuring out which part of the column headers that you are clicking on or trying to interact with, we don't want to apply the vertical scroll offset, because then here it thinks that I'm trying to click further down, but I'm actually at the top. We should only apply the horizontal offset, because as you can see, the headers, they scroll along with the horizontal scroll bar, but they don't move when they use the vertical scroll bar. So this is pretty intuitive as a user, but it's when you actually implement these things, then you're forced to really think about how they actually work. And this is this kind of thing that I keep making these little bugs like this, because it's kind of it's a little bit messy in the head to keep track of like which offsets apply in which situations and stuff like that. So here we're just wholesale adjusting the position, but we should probably have like horizontally adjusted position, which would be the adjusted position's X value, but the original position's Y value. And then we can use that whenever we are looking at the column headers. So where are we using adjusted position? Tilde, blah, blah, blah. If the header rect contains, okay, that's you. Wait. I didn't do this right. I have to say gfx point, otherwise he's not going to know. So maybe I'll write it this way. Okay, and then we need to use it down here as well. Basically, whenever we are testing something, if it's inside a header rect, and then we'll probably need to do this also in the other mouse events. Adjusted position, horizontally adjusted position. And here too. All right. And finally, in mouse down, we'll do the same. Resize origin. Okay, there we go. And let's just try it. Oh, wait a minute, that didn't turn out right. Yeah, we don't track like library dependencies properly yet, so sometimes you have to build twice. But I'm starting to get used to it. All right, so now if we scroll down, then these guys still work. And if I scroll over here, then they work. All right, so that means that if we open up the clock menu applet, fascinating one, and I scroll down to the bottom, I can still resize the page map and admire this beautiful map of the executable, which is just barely half paged in, maybe. Let's look at which one do we want to look at? Audio one? And I'm going to click on it and we'll see if any more of the map fills in, because I'm kind of curious. I feel like nothing happened. Okay. Unexciting. But at least we had the little Easter program, so I'll run that again one more time. So I think this is going to be it for today's video. So if you made it this far, then I thank you for watching and for hanging out while I experiment with this. And I think it turned into something pretty interesting. I like it. And we'll see, maybe it can teach us something, because now it'll always be there, like staring us in the face. Yeah, thanks for hanging out. I hope you saw something interesting, and I'll see you next time. Bye.